Hello everyone. Please let me know if I am completely audible, visible, and my screen is visible to you. Please, anyone in the comment box. Drop a comment in the chat box either I am visible or not, or my voice is reachable to you. Am I completely audible? Please, anyone in the comment box. Okay, so fine. I got a reply from Divakar Pal and he's saying I am completely audible. Okay, and so what is our today's topic? Okay, so our topic is advanced data structure, and we were talking about the range query structures. Range query structures. Okay, so yes, we are doing the range query structure. So in this lecture we start with this problem statement, and we are going to like we are going to say first we are going to do it in by using prefix sum, and then we are going to do it by using our today's topic, that is square root decomposition. Okay, so this is our plan. By using this problem statement only, we are going to understand our topic as well as we'll be solving this problem. So the topic for today is square root decomposition. Okay, so yes, let us first read the problem. What is the problem? So the problem says given an array A and you are given q queries of type. So these are the two queries which we have to perform on that array. The first is sum of L to R. So in this query we have to output the sum of all the elements that falls in this range, that is L to R. And the other query we are getting is update I comma x. So this is updating the element at the ith index by a value x. Okay, now whatever problem we have seen earlier, uh, we are giving only one single type of query. Either we are querying for the say sum, or we are just doing the updates and at last we are querying. So there we were doing this thing. Now suppose if we are doing query online, then how to handle this? Okay, here the queries are online, and what do I mean by online queries? So that means we can get, suppose if we are getting q queries, if we are getting q queries, then this thing means suppose this q is equals to 4, then first we can get a query of type 1, then a query of type, again a query of type 1, then a query of type 2, then a query of type 1. That means we can have a heterogeneous set of this values. Okay, and we have to answer each queries, or we have to modify the array using these queries. Okay, now you remember the problem. Okay, now what we can do, let us start from the naive solution itself. What we can do to solve this problem? Okay, so the naive solution is a very basic approach, like brute force approach we can use to solve this problem. So in the naive solution we just simply do everything that is written in the problem statement. Okay, and we don't apply any kind of logic or any kind of technique here. Whatever that is written in the problem, we have to do this only. Okay, so one more word for the naive is the brute force approach. Okay, so we can, here we are given an array, here we are given an array Now what we can do, so for example, if we are getting a query of type 1, that is sum L to R, then simply we can put our first pointer at the lth position, we can put our second pointer at the rth position, and then we can just simply iterate over these positions and we can calculate the sum of these the elements that is present at these position, and we can just um, give the output of them. So that is how we are going to handle the first query, and the second query we are just going to update the value. We are just going to suppose if the query is like update I comma x, we'll be moving to the index I and then we'll be changing its value to x. So this is what we can do in the naive solution. We are doing exactly the same thing that is written in the problem. Okay, so now this is one way of solving this problem, but is this solution is this solution efficient? Like, can we say that this solution is efficient or not? Okay, so let us first analyze the time complexity of this. Okay, so what is the time complexity here? So let us start with the update. Like update, here the update is a fancy function and we can do this in just order of one time, because we have to just take the value that is present at the ith index and we have to update it by x. So we don't have to do anything here. It is very simple query and we can just do it in the order of one time. So by this method, this query becomes very efficient. But what goes with the second query? So if we have a query of first type, in that case we have to traverse all the elements that falls in this range, that is index from lth index to rth index. So in that case, what could be the worst case? So the worst case would be L equals to 1 and the R equals to n if n is the size of the array. In that case, you have to traverse the complete array, and if you are doing this, then definitely you will be achieving a order of n as a time complexity for this type of query. Okay, now is this query efficient? Like if we have to solve only one query, then this time complexity is not an issue for me, because I would, like in the normal problems, we will most of the times the n is given to like 10 to the power 5. So if only single query would be given, then definitely this thing is possible. But here we are given q queries, and generally in most of the questions that we would encounter, the q would be comparable to n. And if it is the case for processing q queries, and suppose if, like, we have to always think for the worst case. So in the worst case, you would be getting all the, like, you would be getting all the queries of the first type only. So in that case, for all the q queries, you require this n amount of time. So this would be your time complexity, and if this q is comparable to n, then order of n square would be your time complexity. Straightforward. And this is illegal, not illegal, but this we cannot do in 1 second, because here n is 10 to the power 5 and this is 10 to the power 10 operations, and this is not the number of operations which we can do in the just 1 second. Okay, so yes, now can we do a little better than this? Okay, so let us try to apply the concepts that we have learned in the earlier lectures, like prefix structures. Okay, so forget about this. This was the naive solution. Let us try something better. Okay, let us try something better. Okay, so let us apply the concept that we have studied earlier, that is the prefix structure. Okay, now again consider that again consider the same array you are given with. Okay, you will be given some array, you would be having some indices. Okay, now suppose you have created a prefix array on this. Suppose if you have created the prefix array on this, and you know what I mean by the prefix array or the prefix sum array. So in the prefix sum of I, we would be storing the sum of all the elements till the index I. Okay. So everything which I am teaching you is connected, interconnected. So this is the logic we have discussed in the earlier classes. Okay. So someone has commented we can use the prefix sum here, and that is what I am doing currently. Okay. So Ahmed, Arunim, I think he has commented this thing. Okay, fine. So yes, we are using the prefix sum. And how can we come up with the solution using the prefix sum? Because here the issue is with the sum query. Okay, we are not able to get the sum in the order of one time or any time complexity which is lesser than this one. So this sum part was only the issue. Okay, so that's why we have considered the prefix sum. Okay, now suppose if we have created the prefix sum, here we have suppose created the prefix sum. Now what would happen here? Okay, so if we are talking about these things, so this is my prefix array. Okay, now let us again monitor this query, sum L to R. Now what we can do with this sum query? Okay, so now if you have already stored this prefix sum, you can definitely answer this using prefix R minus prefix L minus 1. And what would be the time complexity for this one, for getting the sum from L to R using this prefix structures? So the time complexity for this one is definitely order of 1 constant time. But now if you look update here, the time complexity for update is disturbed now. Okay, how it is disturbed? So suppose now you cannot directly write this update I as ai is equals to x. Can we write this? Anyone in the comment section? Can, like, by writing this only we'll achieve our target, or we have to do something extra? Because if by doing this only, if we can solve the problem, then the time complexity we'll be achieving for this one is order of 1, and this would be the best possible solution. So can we do this? Anyone in the comment section? I'm not asking about the time complexity, I'm just asking can we do this with the prefix sum? We can just change the, we are just changing the element that is present at the array at the ith index, the element at the ith index. So definitely not, this is wrong, we cannot do this. Because if we are doing, okay, so Arunim has said no, because we have to update the whole array, and this is what the solution is. Because if you are doing this ai is equals to x, then this change or this updation is getting reflected only in the original array, only in the array, original array, only in the original array. But this change is not reflected in this prefix array. Okay, so this change is not reflected in this particular array. So you have to reflect whatever changes we are making in this original array in the prefix array also. Otherwise this thing would be useless and it would make no sense. So for that, suppose if this is your ith index where you have to make a change, and if suppose originally there were and the y element is written here, now if you are changing this y to x, now after all the prefix sums that falls after this ith index, like I plus 1th index and I plus 2th index and I plus 3th index, all of this is getting disturbed because here the value is changed. So the prefix sum after that would get changed. Okay, so what we can do is, here originally the value was y and now the value is x. So the x minus y difference is created now. So we have to update this original array by x, and then we have to update this sum in all the indices after which falls after this ith index. Okay, so then we have to maintain this prefix sum. And now if you look here, in the worst case you would have to like update the first prefix sum only, and in that case you have to after if you are updating the first index, then in that case you have to update all the prefix sums from the first index to the nth index. Okay, and this would cost you order of n time. So now the sum query, using the prefix sum, the sum query becomes efficient, but this update query becomes inefficient. Now this thing is inefficient. Okay, this query becomes inefficient. Okay, and you have, say you have improved your approach, and then we have tried to use the prefix structure, but here also we are getting some problems. Here the sum query becomes, we need square root decomposition, and from this point our topic starts. Okay, someone is saying my screen is lagging. Okay, let me check. Okay, people are commenting that my screen is lagging, and this is because of, okay, so now is it working correctly? Anyone in the comment section? Is it lagging? Okay, I think now it is fine. I'm getting good speed. Anyone in the comment section, please tell me if I am still lagging, or is everything fine now? Anyone in the comment section? Okay, so ECAF Eman has commented that now it is working fine. Okay, so fine. Now let us start with the better solution. So now, what is the idea of the square root decomposition? So the idea is, if we are given this array, okay, so if we are given this array, okay, now what we are going to do is, we are going to break, we are going to break this array, or say we are going to divide, we are going to divide this array, we are going to divide this array in some number of chunks, or say blocks, some number of chunks, or say blocks of size sz. Okay, now for solving this problem, what we are going to do is, we are going to take, we are going to divide this particular problem in, say, some number of chunks. Okay, suppose if this is the problem, and the the size of each chunk, the size of each chunk is same, that is sz. But here we have an exception, the last chunk can have the different size, but for all the other chunks the size is going to remain the same, that is sz. Okay, now so suppose if we have divided this into some number of chunks, if this is my one chunk, and if this is my like third chunk, so let me take it with the another colors so we can differentiate. Okay, so suppose if these are my chunks, or say blocks, in which we have distributed our complete array. Now suppose if I am calculating the sum for each chunk. Okay, now this array, this complete array is just divided into four chunks. This is my one chunk, this is the other chunk, this is the other chunk. Okay, and this one is the last chunk. So suppose the indices for them is 0, 1, 2 and 3. Okay, now suppose if I have calculated the sum of each of this chunk. Okay, suppose here we have this S0, S1, S2 and S3. S0 is denoting the sum for chunk 1, S1 is denoting the like this one, S0 is denoting the sum for the 0th chunk, S1 is denoting the sum for the like sum of all the elements in the first chunk, S2 is denoting the sum of all the elements that falls in the third chunk, second chunk, and S3 is the sum of all the elements which falls in this third chunk. Okay, now what we can do, now suppose if again we are getting the same query, that is sum of L to R. Again if we are getting the same query, now what we can do, suppose if my L was originally at this point and my R was originally at this point. Now we don't have to just go through all the points. Okay, like uh, what are the elements that is going to fall in this L to R range? So these are all the elements that is going to fall in L to R range. Okay, now these are the elements that is going to fall in L to R range. Now do we need to calculate the sum of all these elements to get the result? No, we can just get the sum of these elements just by referring to the these two values, the sum of these two chunks. Okay, the sum of these two chunks, we can just sum up these two chunks and we can get back the result of all these six elements. Yeah, initially what we were doing, we were taking the sum of all these six elements, but now here we are just taking the sum of these two elements. Okay, and we can get our results. So suppose if the lth and the rth position is placed at the end point at both of these chunks, then we can just do it in the like taking the sum of these two chunks only, and initially we were taking the sum of these six elements. So definitely the number of operations has been reduced. But now suppose if the L is not at the end points, if L is here and the R is here, then first you have to take the sum of each chunk. Then you have to take the sum of each chunk, and all the elements that is remaining, you have to calculate the sum of these elements manually. So here we cannot like understand how much time complexity it is decreasing. But we specify if we specify the size if we specify the size, so what I'm saying is, if I specify the size of the block, then we can note the drastic change in the type complexity. Okay, so suppose if n is the size of the array, if n is the size of the array, then I am saying the square root of n is the optimum size of the chunk we should take. Okay, this is the optimum size of the chunk we have to take. Okay, okay, now okay, someone has asked like how much time does it take to do DSA at best level. I am currently at linked list part. Okay, so that is a, yes sir is reading the chat, yes definitely. Okay, so yes, it is a relative question, like how can I tell you like how much time do you take? I can tell like how much time do I take, but it is just totally dependent on your grasping power, like how much you can learn in a single day. So, and if you are doing good practice, I don't think so it requires more than 2 to 3 months to be to get a good hold at the data structures. uh, now it's totally dependent on you. Okay, so now where we were, so we were talking about the optimum size of the chunk. Now why we should take always take the square root of n chunks? Okay, so now suppose if we are having an array, and if we are reducing, now what would happen if we are having, so this thing is very intuitive. Okay, so I am explaining it in the intuitive way. Okay, I'm not going into mathematics, just by intuition you can understand it. So if we are reducing, so suppose this SZ is the size of the chunk. Now suppose if we are reducing the size of the chunk, okay, that means the chunk size is smaller than the square root of n. Then in that case we would be having a large number of chunks. And if we are like, if we have to sum up the large number of chunks, then and then also the time complexity is going to get increased, because there we have to process the large number of chunks. Now suppose if, okay, now suppose if you are increasing the size of the chunk, then what would happen? So if you are increasing the size of the chunk, suppose now if this much is each size of the chunk. So if you are increasing the size of your chunk, and now suppose if an element falls, like if you have to calculate manually also for the incomplete chunks. So if this is the incomplete chunk, and if you have to like calculate the sum manually, so in that case you have to visit a large number of individual elements. So in that case also the time complexity is going to get increased. So it would fall optimal on in if we take just the square root of n as the block size. Okay, so now what we are going to do is pretty simple. It is very simple. What we are going to do is, so suppose if this is your array, now we are going to divide it in some number of chunks, and each chunks represent the sum of the all the elements that falls in that particular chunk, and the size of them is square root of n. And if this is the case, now let us analyze the time complexity for this one. Okay, so now let us the time and analyze the time complexity for this one. Okay, so what would be the time complexity? Okay, so we have two operations. First is sum, L to R, and the other one is, okay, and the second value is update. The second query is update L to R. Okay, someone with the name Ekef Aman has mentioned uh, like a mathematical approach for this problem also, like the time complexity, if the size of the chunk would be sz, so numerically the time complexity would be n by sz plus sz. So this would be the time complexity. So if you are going to increase the sz, then this part is like this part is going to get increased. So in that case also the time complexity is going to get increased, and if we are decreasing the sz, then this part is going to get increased. So again the time complexity is going to increase. So we have to take it at some optimum level, and that falls to order of square root of n. So yes, this mathematical approach is also correct to understand the time complexity. Okay, now so if we are talking about the sum of lr, so in that case you have to visit like the worst case would be you have to visit like the total number, like if tot is the total number of chunks you have created, then the worst case would be you have to visit the total number of chunks minus 1 chunks, and the like and the value and the value that you have to calculate is also the size minus 1. Okay, so in that case, for both of the operations you have to go to the square root of n as a time complexity. So that would be, the worst case would be square root of n plus square root of n, and that would be 2 into square root of n. Now, so the time complexity, we can say that this time, the time complexity for this operation is order of square root of n, and by using this mathematical function also you can get this result. So n divided by square root of n plus square root of n, and this thing would be again square root of n, so this comes out to be 2 into square root of n. Okay, and now what would be the time complexity of this update function? Okay, so suppose if I am talking about the square root function, the time complexity for this update function would again be order of square root of n, because in that case, if you are making changes in original array, somewhere in the original array, so suppose if this is the point where you have to make the changes. Okay, so suppose if you are making change here at the ith index, then you would be doing just simply ai equals to x, and now it won't be order of square root of n, but it would be order of 1. Okay, because in that case you don't have to visit all the chunks to make the changes. We don't need to do that. We have to just visit the chunk that it belongs to, and we have to change the sum here only, and this we can do in just order of 1 time. Okay, so now you can compare, this is pretty efficient, these two operations in this is pretty efficient. How we can conclude this? Because in that case, like if we are processing the q queries, and say the time complexity for each query is t, then the time complexity for all the queries would be O of qt, and if say q is comparable to n, the time complexity would be order of n, and here we are taking the square root of n time, so the time complexity would be square root of n. Okay, and if n is given to you is comparable to 10 to the power 5, then the time complexity falls in order of 10 to the power 7 range. Okay, so this we can run in 1 second, not in 1 second, but definitely in 2 seconds. Okay, so this is what we are going to do in the square root decomposition technique. So this is just to understand the time complexity we are reducing by using this square root decomposition technique. It is an advanced technique that we can use to solve the range query problems. Okay, and here we are taking the range sum problem. So any doubts till this point, anyone? Okay, so let me revise that what we have studied. We have taken this problem, that is the range sum problem with point updates. Okay, and first we have taken the nice solution. Here we are getting the order of n time for sum and order of 1 time for updates. So this we have considered, marked as the inefficient solution. Then we have taken the solution for the prefix sum, and here also we have we have monitored the time complexity for sum and update. So the time complexity for sum is coming out as order of 1 and update as the order of n, so that is also we marked as inefficient. And now we have seen this square root decomposition technique. Here we are getting the time complexity as order of square root n and order of 1 as the sum as the as the time complexity for the sum and update. So that we have, that is something efficient we can do. Okay, now any doubt till this point, anyone, please mention in the comment section. Okay, now functions we need. Can you share the problem ring related to this concept? So like I have searched this, it is very standard problem. You can, like you can search the GFG portal, there also we are having this problem, but you can search it and you can google it. This is very standard problem, you can find it anywhere. I would prefer solving it on GFG portal. Okay, now the functions we required in this data structure. Okay, now the first thing is we require a update. Okay, now the second function we require is query or say sum. So for update we would be passing an index, and we would be passing a value. Both of them would be integer type, and in the query we would be passing two integers, that is integer left and integer right. Okay, so these were the two functions that we need to implement in our data structure, and the third function is preprocess. Okay, so when we will be given an array, first we have to preprocess it to divide it into the chunks and to take the sum of the chunks. Okay, so these three functions we have to implement using the to implement the this technique, this square root decomposition technique. Okay, so let us take the like each of the functions one by one. Okay, so first update. Okay, so in the update function we just have to suppose if block is representing the chunks, and if a is representing the given array, and if sz is the size of each chunk, then first then which chunk it belongs to. Like, how can we know that if the index of the given query is ind, then which chunks it belongs? So it would belong to ind divided by sz chunk, and then we have to refer to this chunk, and we have to subtract the original value from like a index what is stored there. So we have to first subtract this value, and then we have to update the value here to x, and then we have to update this chunk. Okay, so the three operations involved here is uh, suppose if block is storing the chunk, then block of index by size minus equals to a of index, then we have to update the a of index by a value of x, and then again we have to add it in our current chunk, that is this thing. Okay, so just by doing these three operations we can implement our update function. Then the second function is query function. So for query function we can have three things. Okay, okay, suppose these green blocks represent the chunks. Suppose these green block represents the chunk. So first we have to take 2 points, that is the left and the right. So the left point would be pointing to the first complete chunk we have to add, and the right would be pointing to the rightmost chunk, the rightmost complete chunk of whose sum we have to take. Okay, and suppose this L and R are the query limits. Okay, so these are the complete chunks we can take, and then we have to sum up these elements individually. Okay, so here we need to do three things. We have to run three for loops. Okay, we have to run three for loops. So one for loop would be for calculating the individual sums that falls below this left complete chunk. Okay, so these two elements would fall this below this left chunk, so we have to add this. So for that we have to take a for loop, and then all the elements that falls in this left right uh, between this left and right is the left and the right limit of the chunks. It is the indices of the chunk whose sum we have to take. Okay, so then the second for loop would be to take the sum of the chunks. Okay, sum of chunks. and then the third for loop would be taking the individual sum of all the elements which falls beyond this right complete chunk and before this right limit of this query that we are given with. So and if we are doing this and then we are if and after doing all these sums from this for loop, these three for loops, we would be returning this sum and that would be our final query. Okay, and before doing these two queries, first we have to implement the this preprocess function. Okay, and this function would be creating a chunk. Okay, so if you are given n as your array size, then first you have to take sz as equals to s cube rt of n, that is square root of n, and then you have to create another vector, say block, which is of the size sz to store your chunks. Then in each chunk you have to store the sum of all the elements that falls in that chunk. So this is what you have to process. Okay, so this is what we are going to do in the preprocess function. So now let us implement this. Now the theory part is complete. Now we have to implement this thing. We are going to implement this particular data structure and we are going to implement these three functions in this particular data structure, and by using this we can solve this particular problem. Okay, so I am using this text editor which I mostly use, that is Sublime. So if anyone having any doubt in the theory part, please comment in the drop a comment in the chat box and I would be more than happy to solve this. Otherwise I am coding it as we are running out of time. Anyone, any doubts? Prabhat Guring is saying no problem. Okay, fine. So we need three functions. One is update. Okay. The another one is the query. And in the query part we have to pass the left and the right limit of the segment as integers L and R. And before that we need the another function that is used for pre-processing. Okay. Okay, we'll be taking two vectors. One is for storing the array, the other one is for storing the chunk. Okay, we need two integers also to store the size of the array, given array, and to store the size of the chunk. Okay, so let us first write our driver function. So we'll be taking an array as the input. Okay, so we have taken our input array and then we have to declare our size as square root of n. So the size of the blocks would be square root of n, and then we have to create a vector for the block also, and for this the size would be sj. Okay, now what we have to do in the preprocess function. So in the preprocess function we have to sum up all the elements of a particular chunk. So they would be, we would be having sj number of chunks, sj as a size of chunk, and some number of chunks we would be having, and for that we have to sum each element that belongs to the current chunk. Okay, so we'll be traversing all the elements, okay, like this. And if I is the index of the current element, then what would be like its, what would be the index of its chunks? So the index of its chunk would be I by sj. Okay, so we are going to increase. Okay, so initially the sum of all the chunks would be 0. Okay, and as we are moving, the sum of each chunk, like we have to sum up all the elements into their corresponding chunks. So this would do the exactly same thing. So now our, like we have pre-processed everything. We have now the block of I by sj is storing the corresponding the sum of the corresponding chunk. Okay, now what we have to do in the update section. So in the update section, the block, okay, so this ind is the index of the element that we have to update. Okay, so what would be the chunk, like what would be the index of its chunks? So the index of its chunks would be ind by sj. Okay, now we have to take this block, like we have to subtract the previous element from this chunk. So that would be uh, a of ind, and then we have to update this a of ind with a value of x, and then again we have to update our block, that is block of ind by size plus equals to a of ind. Okay, now do you think this would update my mm, my original array as well as my block chunks? So yes, definitely this would do the same, because here it is updating the original array, and using these two statements it is updating the, using these two statements it is updating the chunks also. Okay, now we have to query. So for query, first we have to declare a variable to store the sum of the query. Okay, fine. Now first we have to calculate the left and the rightmost complete chunks that we have to take. So for that we can declare this int, that would be left, and this is l by sj, that would be the index of the leftmost chunk that this element falls in, but that would be definitely a incomplete chunk, and we need all the complete chunks. Okay, so for that we have to increase this left by one value and decrease the right by one value. Now we can guarantee that this left and the right is storing the chunk, that the complete chunks that falls in our range. Okay, so yes, and then we have to move for the complete chunks. Okay, and then we have to sum it up. Okay, so we have taken the complete chunks. Now what we have to take is all the individual elements that falls in the right. So for that, what would be the starting index of the next chunk? So as this right was the complete chunk and the last complete chunk we have taken. So the right plus 1th chunk would be the chunk we are targeting. Okay, and we are not targeting the chunk here, we are just targeting the individual elements. So to get the index of the individual element, we have to multiply it with the size. Okay, and this should be less than equals to this particular index plus will be taking the modulo of r with the sz. Okay, so this r modulo sz would be giving us the number of individual elements that we required to take sum of. Okay, because because this right is just storing the complete chunk whose sum we have to take. Okay, so it is not storing the number of individual chunks we have to store, no, whose sum we have to store. Okay, for that we have to take this thing, and then okay, so here we will be taking the sum a of I. Okay, now this is done. So we have taken the sum of all the right individual elements. Now let us take the sum of all the left individual elements. Okay, so that would be int of I, so that is this left. So the left is the leftmost complete chunk, but we don't have to like stop there, there may be some individual elements beyond this point. Okay, so we have to take the sum of those individual elements also. So for that, this would be left into size minus L modulo S. Okay, so here we are just taking R modulo size because we are moving right. So and here we as we have to move left, we cannot take the simple modulo. The simple modulo is for moving to the right. So if we want to move to the left, we have to subtract this modulo from the size itself. Okay, so that is we have to take, and it should be less than left into sz, as this we have already counted, and I increment. Okay, and that would be, we'll be taking the sum of this thing. Okay, that is sum plus equals to ai. Now someone is saying that my voice is very low. Okay, I'll try to speak louder. Okay, so yes, we have to take this sum. Now we have taken all these three for loops. One is for taking the blocks, and the other one is to taking the left individual elements and the right individual elements, and then we have to return the sum. So we have updated, like we have implemented all the three functions that is required in it: the preprocess one, the update one, and the query one. Okay, so let us preprocess. Okay, now let us check if the code is working correctly. So let us take some 10 elements. Okay, so we haven't took a semicolon here. Lots of mistakes. Okay, so yes, in the line number 26 we have written s somewhere instead of writing sz. Okay, so this thing should be ested. Okay, now I think it is working. Let us check for a query. So 0 to 9, or say 0 to 6. So it is giving 13. Let me check. I am making some error here. Because, okay, so let me check for another queries. Like, we have to test where our code fails. Okay, so it is not giving the correct result. Why? Am I taking the correct array? Let me check. Okay, so the input array is correct. Then let me print the sum of each blocks. Okay, so nothing is getting added in the block. So that is the problem. Okay, so why nothing is getting added? Let me check. We have called preprocess function and still we are getting this. Okay, so because here we are referring to the wrong n. Fine, we should not take this n because this is the local n and here we have declared a global n, so we have to take that n only. Okay, now let us check. Okay, now I think it is working fine. Okay, again it is giving the wrong result, but still I am pretty sure that my block is storing the correct results. As you can see, for 10 the square root would be 3 and the sum of first three elements is 1 2 3, that is 6 again. 4 5 6 is 15 and 7 8 9 is the 24. Like 9 and 8 is 17 and 17 plus 7 is 24. Yes, and we will be leaving this 10 behind because we don't need that. We would be taking it as an individual element. Okay, so fine. Now here we are making some mistakes. So fine, let me check what is the sum here. Okay, so for 0 to 6 it is giving us 20 as a result. Let me check. So 1 2 3 is 6, fine. 6 plus 4 is 10, fine. 10 plus 5 is 15, fine. 15 plus 6 is 21, and plus 7 28. It is giving the correct result. And let me check for the another query. 25 for 2 to 6. Okay, so for 1 to 6 it is giving the correct result, that is 28. And now for 2 to 6 we have to check this query. 3 to 7. Okay, and for this one it is okay. We can subtract this thing from the original query, that is 28 minus 3 25. Okay, yes, we are getting the correct result for this still. Okay, now we can take a update query. So let us update the value that is present at the second index by a value. Say here initially it was 3, let us make it 5. So the difference we are increasing is of 2. So let us check if the output we are getting is 27. Okay, so this is definitely 27. So I got my mistake. What I am doing wrong is, if after doing this, if left is equals to right, then we have to do something. Okay, if left is equals to right, in that case the left is going beyond the right, and the right is like, in that case the right would be less than left. So this is the case it is not handling. Okay, so in that case we have to just move from all the way int l. Okay, r, and I increment, and then we have to take the sum. Okay, and then you have to return the sum from this point only. So for this query, okay, for this query we were getting the wrong result for 0 to 0 query. Let us check this one. Okay, now we are getting the correct result. So that is one thing we have missed. Like, if left is equals to right, in that case you have to handle it separately, otherwise you would be losing your left and right, because right would become less than left. So that in that case this thing won't work. So you have to handle this as your base case. Okay, so now this is the code for the uh, square root decomposition. You can solve a lot of problems using this square root decomposition. And in the next sections we would be studying about the Fenwick trees and the segment trees, which can give the exactly same solution in a bit less time complexity, which reduces the time complexity to a logarithmic factor. Here we are getting it in the square root of n. So we'll be discussing this in next streams. Okay, so this is the code. There we have, like, by coding this problem, we have learned a lot of things. Like, you have to, like, you can learn from the thing which I have done here. Like, you have to never miss the base case. You have to always think for the base case. If you are getting the wrong result, then probably you would have missed some base case. Okay, you must have missed some base case, so you have to think for the base case also every time you are coding. Okay, so this is all for today. We are stopping here. Thank you for joining. Any doubts you have, please drop a comment in the chat box. I would be solving it. More than happy I would be. Okay, anyone having any doubt, please write in the comment box. We have finished, like, whatever the content is there for today's lecture. We have finished all these things. Any doubt you are having? Anyone? Okay, as we are not getting any doubts, we are stopping our stream. Thank you.